Now, this quantum mechanical stuff, um, that's the hardest class I've ever taken. And I went into quantum mechanics with a very high B average at Davis. First test, I got a C minus on it. I was like, oh. And it's just a hard topic. And the guy that taught it, they named the lecture hall in Davis after him. His name is Peter Rock. And man, that guy was hard. And it's a whole quarter class or a semester, depending on what your school is organized over. So we are going to cut that way back. And you don't have to do differential equations. You don't have to do triple integrals and all that junk that goes with quantum mechanics. We're going to do a nice kind of breeze over it to give you an idea of what's going on. Okay, I'm going to start with Bohr. Now, if you remember Bohr, Bohr said there was a nucleus and there were planetary-like orbitals around that nucleus. And that's where the electrons resided. Now, what some of the things Bohr said is the closer the orbital is to the nucleus, the more stable it is. That's because, as you know, in the nucleus, there are protons and neutrons. Protons are positive. Electrons, as you know, are negative, so they attract. That's why the closest one is the most stable. Secondly, because it's also the smallest, it can only hold 2 electrons, max. The next one out is bigger, so it can hold 8. And then 18, and it grows from there. Now we are going to name those orbitals. As a shell. So we have shell 1, 2, 3, 4, 5, 6, 7. 1 through 7. So this is shell 1, shell 2, 3, etc. Now, if we look at lithium, lithium has 3 electrons. So the way they're going to reside in those orbitals, they're going to first populate the most stable orbital, which is the innermost one. So that means 2 of those are going to go in that first orbital. Then we have 1 left over. So that's what lithium is going to look like. 2 electrons in the inner one, the next one out in shell 2, we have 1 electron. Now, we're still talking Bohr now. We're not talking quantum mechanics. One of the problems with Bohr's model is his theories only work with hydrogen, 1 electron. When we get to helium, his theories don't work. So that's why the quantum mechanical model came along to kind of fix Bohr's limitations. Okay, one thing that quantum mechanics says, shell 2 is not 1 orbit. It's many orbitals. In fact, there are 4 suborbitals for shell number 2. And those suborbitals are called subshells. So shell 2, 4 subshells. Shell 1 has got 1 subshell. Shell 3 has got 8, a whole bunch more. 9, actually. Okay, so we're going to work on the first 2 shells in the beginning here. Now, quantum mechanics labels every single electron in the atom. So with lithium, we have 3 electrons, 3 labels. Now, let's look at the periodic table here. That's shell 1, or period 1. Shell 2 and shell 3. So notice where lithium is. Lithium is in shell number 2. That means there are some shell 1 electrons in lithium. These guys here. So shell 1 electrons are called S block electrons. And there are 2 of them. Okay, so the way we're going to label these, let's start with the first 2 electrons. Shell 1 the subshell electrons are S, and there are 2 of them. Okay, so that's the shell. And that's the number of electrons in the shell, or in the subshell. Okay, we have 1 more electron to go. So we've accounted for 2 of the electrons. Now, lithium resides in shell number 2. And we have 1 electron left over. So that's the electronic configuration for lithium. We've accounted for all 3 electrons. 2 of them are in shell 1, subshell S, and there are 2 of them. The last one resides in shell number 2, S subshell, and there's 1 in there. Now, the other thing about quantum mechanics is there are shapes to the orbitals. Think of the S as sphere, S-P-H-E-R-E. In other words, it's round, it's evenly distributed around the nucleus. All the other orbitals are not. They have definite shapes, and some of them are quite strange. Okay, so when we found shell number 2 has 4 suborbitals. The first one is called S, just like shell number 1. That takes care of 2 of the electrons. Remember, this can hold a total of 8 electrons. 2 in the first shell, 6 in the next one. So the S takes care of 2. And the next set of orbitals that have to take up the slack on the rest of the electrons are called P. Now, P is broken up into 3 suborbitals. and they align along the XYZ axis. And there are 2 in each orbital. So that's how we came up with shell number 2 having 8 electrons. Okay, so let's look at oxygen now. Okay, oxygen, as you know, has got 8 total electrons. And it's in shell number 2. Okay, so the first 2 electrons of the 8 is going to go on the most stable of the orbitals. Okay, shell number 2, because we have 6 more electrons to account for. So we're going to put 2 electrons there first, because the s orbitals are closer in than the p orbitals for shell number 2. So those fill up first because they're more stable. Okay, then we have the p subshell, and the p subshell can fit 6 electrons total, but each orbital can only hold 2 electrons max. So if we can fit 6 electrons in the p orbitals, how many electrons per orbital can we put in there? 6 divided by 2, 6 divided by 3 is 2, exactly. So each p can hold maximum 2 electrons. Okay, and the way we fill those p suborbitals is 1, 1, 1. We have 1 more to go, or 2 more to go. 1 more to go. So the 1 becomes a 2 here. So the electronic configuration for oxygen's electrons is 1s2, 2s2, and how many p electrons are there? 4. So that's the electronic configuration for oxygen. Now notice the superscripts 4, 2, 2 add up to 8. So we've accounted for all 8 electrons. Now, remember when we're doing Lewis dot structures. That's what the valence electrons look like for oxygen. We have 2 pairs and 2 singletons. Now, this is the valence electrons here. Outermost orbital. Okay, notice we have pair, pair, singleton, singleton. That's where this comes from that there. Now, the exception to all this is carbon. Carbon's got 6 electrons total. So let's do the electronic configuration for carbon's electrons. Okay, so we have 2 of the 6 goes in shell 1. Then we have shell 2. 2 electrons go in the s. Then we have 2 more electrons. Notice there are none in the z, only in the x and the y. Now this officially, if you look up online, it depends on how sophisticated the site is. They'll give you this as the electronic configuration. Now, going back to Lewis dot structures, how many singletons does carbon have? 4. That doesn't agree with us at all. This says carbon's got 1 pair and 2 singletons. So what happens with carbon? Carbon does something wild. Carbon undergoes something called bond hybridization. What that means is we're going to take these suborbitals and modify them. Once they're modified, and there's a whole hour lecture on how that modification undergoes, what happens with carbon, and that's the exception, carbon only. It looks like this. We end up with the hybridized names of these orbitals are sp3. And there's one electron for each one. That's how we end up with 4 singletons. Okay. Now, that's all you need to know about bond hybridization. In your next class, particularly if you take 1A or 3A, you're going to get this quite a bit. But as far as our class is concerned, Lewis dot structure carbon's got 4 singletons. This is why. It's all you need to know. Okay. Not why or anything like that. Now, bond hybridization happens a fair amount, but the most noticeable one doing early Lewis dot structures is carbon. Carbon should have 2 singletons and a pair. Doesn't. So we have to explain why it's got 4 singletons, and this is why. Yeah. No. His question was, do we need to know this, right? No. But this is why I know in the back of your mind, you're saying, well, wait a minute, Ferguson. We just went through this whole thing on Lewis dot structures. Carbon's got 4 singletons. This is why. Okay? So don't worry about knowing it other than carbon has 4 singletons. And you'll study this in depth. And when you get to organic chemistry, for those of you in allied health and those of you who are in STEM, you're going to get this out the yin-yang, bond hybridization. Okay. So this is officially what carbon is going to look like if I ask you for carbon on the test. That, not the hybridization version, okay? Now, we look at that, going back to oxygen. Frequently, we talk about orbitals. And the way they do orbitals is they go like this. So 1, 1, 3. This is shell 1, shell 2, shell 2. These are S's, and these are the P's, X, Y, Z. Okay, so oxygen has got how many electrons? 8 total. Okay, so we're going to put 2 here. And those arrows are electrons. Notice the arrows are opposite. That's because electrons have a magnetic component to it. So think of electrons, besides whizzing around really fast, they also are whizzing around magnets. So what happens when you put 2 magnets together? There's a good way and a bad way, right? What's the bad way? All of you have done this with magnets, yeah. What? Yeah, so if you put the North Pole and the North Pole together, what happens? It repels. So what's the most stable way to put 2 magnets together? North to south, south to north. That's what the direction of these arrows indicate, north and south. Now, if we put north-north, that's an unstable configuration, which doesn't happen. Only the stable ones happen. So they've got to be opposite. Okay, so 2 electrons goes in shell number 1. 2 electrons go into shell number 2. We're just following this here. And then we've got 4 electrons in the p's. Now, when we have multiple suborbitals, the way we're going to fill them is 1, 1, 1. We have 1 more to go, like that. So we've got pair, pair, singleton, singleton. So this is the orbital version of the electronic configuration for oxygen. Now, some books use squares. To me, circles are easier to draw. But they're the same thing, though. They're representing the suborbitals. And again, those p's lie along the XYZ axis. Okay, so on a test, let's do electronic configuration for oxygen. That's what I want. And you will be tested on that. Where'd he go? He left. Okay, so before I get to shell 3's got some little nuances. Now, shell 3 holds 18 electrons, not 8. So how are you guys with this? Tell me how you really feel. Okay, let's do some more shell 2 before we go on to shell 3. Let's see. Let's do fluorine. Okay, how many electrons does fluorine have total? 9. So we have to count for all 9 electrons. Now, in a minute here, I'm going to show you what uranium looks like. How many electrons does uranium have? 92. So uranium's electronic configuration is quite long, but every single electron is accounted for. Okay, so we have 1s, 2s, 2p. So of the 9, let's put 2 in the 1s shell, 2 in the 2s subshell. That's 4 of the 9. Now we're going to split the next 5 in the p's. So 5 plus 2 plus 2 is 9. So we've counted for all 5 or all 9 electrons. Now, let's look at the orbital view of that. Five here. 3, 4, 5. So fluorine now, this is the valence over here. This is the core electrons here. According to this, we have 3 pairs and one singleton. Now, when you're doing Lewis dot structures, three pairs, 1, 2, 3, one singleton. Okay. Any questions on that? Okay. Let's look at neon. Neon's got 10 electrons. Let's go right to the orbital one. Okay, we have 2 electrons in the 1s, 2 electrons in the 2s. That's 4. So we have 6 electrons for the p's. Now, remember we talked about the noble gases. The noble gases are extremely stable. This is why. Are there any electron pairs? We have lots of them. Are there any singletons? No. No singletons. That means it can't bond with anything. There are no singletons, it can't bond. So neon is happy the way it is. Everything else has singletons. They have to bond to become more stable. And this is why neon is so stable. When this happens, it's called a full shell. Now we're talking about the valence orbitals, which are these here. The ones are core, valence. Now everything depends on configuration of the valence electrons. So we've got full shell. The 2s are full, all the p's are full. Super, super stable. No singletons. And all the noble gases have the same valence setup. And that's why the noble gases are so stable. And yes, you can be tested on this. So make sure you understand that, why there are no singletons. Okay, why don't we do let's look at by the way, we're going to be doing elements from shell 4 up. Nothing past shell 4. No shell 5, 6, or 7s. Let's go to shell 3 now. Now shell 3 is odd because it jumps over. There's an anomaly with shell 3. Remember I said shell 3 can hold 18 electrons? Oh, this thing keeps blinking off. Okay, so let's look at aluminum. Now, aluminum's got, well, 13 electrons. Now, aluminum is in shell 3. So that means the core electrons are shell 1 and shell 2. Okay, so when we fill up shell 1 and shell 2, we've accounted for 10 electrons. That means we have 3 left over. Did everyone see where I got the 3 left over? Shell 1 takes 2. Shell 2 takes, how many does shell 2 take? 8. So that's 10. And there's 13 total. So that's 3 left over. We're going to fill the S's first. And 1 left over in the P. So if we did a Lewis dot structure for aluminum, 1 singleton, how many pairs? 1 pair, 1 singleton. Now, remember I said shell 3 has got 18 electrons possible? Those are called Ds, the remaining 10. But those are empty because we don't have enough electrons to go around. But if I fill up all the shell 3 places to stick electrons, orbitals, it can hold 18. 2 for the S, 6 for the P's, 10 for the D's. Now there are 5 orbitals for D, 2 electrons for each one. That ends up 10 electrons. Possible. Okay. Now the question is, do I mark down the D's even though there are not enough electrons to go around? Usually not. Usually they don't include the D's that are totally empty. Or if the P's are totally empty, they usually don't include them. I like to put them down just to be complete. So let's do sulfur. Okay. Sulfur's got 16 electrons. And we're going to spread them out over shell 1, shell 2, shell 3. Okay. So we're going to go 2, 4, 10. We have 6 electrons. Bless you. Okay, so this has got, so these are core. That's valence. Now think about oxygen. Remember, oxygen has got remember, 2 singletons, 2 pairs. Sulfur is right underneath oxygen, and its chemistry is the same as oxygen. So guess what? It's the same. Sulfur and oxygen have the same electronic configuration. Okay, we've got pair, pair, single, single. Pair, pair, single, single. And that's why sulfur has the same chemistry as oxygen. Its electronic configuration is the same. Two singletons, very unstable by itself. Got to get hooked up to two other elements or a double bond, one of the two. Okay, so are you guys feeling a little better about this? Okay, so let's now to net this out in the most simplest terms possible for quantum mechanics. Quantum mechanics says that any electron can be described with four parameters. That's the shell, subshell, the number of electrons in the subshell, and the spin of the electron. And when I say spin, I'm talking about the magnetic direction, north or south. These are the four variables for any electron in our universe at this present time. Okay, now we're going to get interesting. Let's do iron. "26 electrons. Now, when we get to shell 4 is going to have some D's in there, need to be filled. Okay, so the 26 electrons. So we have okay, that's what iron looks like. Now again, core, valence. Now the problem is that I said the s orbital fills first because it's closer than the p's or d subshells. So when you look up the electronic configuration for iron, it's going to look like this or that. Usually this one here. And this says, this is going to be the same. This is the valence here. So first fill those, the inner S is closer than this S. So this fills first, then the P's, then we fill the S's, which actually is closer to the nucleus than the D's. That's why it fills first. Then we have the leftovers into the D's. Yeah. No. Four of them are one, and then the first one is a double. So because there's five, and there's 60 electrons. So there's you put five across and then start pairing them up. Okay, so that's what iron looks like. Now we're not going to go below that because they get more and more complicated. But for our class, I want you to understand that this was a big deal upwards of 120 years ago. Einstein was running around, de Broglie, Schrodinger. Remember, you've heard the thing about Schrodinger's cat? This is the basis of a lot of that. But this was a big deal because this started explaining things better than Bohr. Or he got a Nobel Prize for it, but some of the things didn't work out with Bohr's model, except for hydrogen. When we started getting more than one electron, it didn't work so well. This model works quite well for multiple electrons. Okay, let's do one more shell 4. Let's do I don't know. Let's do zinc. Twice is a charm. Are there any questions about iron? Yeah. Yeah, shell 4 gets kind of weird. I said for shell 3, 18. So it goes 2, 8, 18. And the 18 is when you add the 10 electrons from the Ds. And then it goes to 32 and gets, because the orbitals become really far from the nucleus, so they can hold more electrons. Okay, so we're going to do zinc. And zinc's got how many? Oh, let's see. 30. So we have to count for 30 electrons. So if we count up 10, 18, 28, 30 electrons. So the superscripts have to add up to the total number of electrons. And again, shell 2 is core. Now, zinc is a pretty stable metal. Not like a noble gas, but it's more stable than a lot of the metals. So you frequently can find zinc metal in nature. Notice there's no 4Ps. No 4Ps. So that means it's not a full shell. But we have a full subshell, which is more stable than not having a full subshell. Okay, so that would be zinc. Now, when we get to ions, these are neutral. We haven't talked about ions yet. There's electronic configuration for ions as well. So when you have a cation, that means you're missing electrons. And the question is, which electrons go? So zinc forms a +2 ion. That means it's missing 2 electrons. Which 2 go? Which are the least stable? Those are the ones that go. Look at the configuration up there. Which is farthest from the nucleus? This guy. So the zinc +2 cation, it's missing the 4s electrons because they're farthest from the nucleus, the least amount of attraction, so they're easiest to leave. In fact, the only ion that zinc makes is zinc +2, mainly because the subshell is full, very stable ion. Now, when you get to 1A, particularly, you're going to talk a lot about ionic electronic configurations because there's a whole host of things can happen in here, a whole bunch of nuances. Okay, but that's just as a harbinger of what's to come. Zinc is a real easy one to explain. That 4s2 electrons orbital is really far from the nucleus. Yeah. Normally, no. Normally, you can always lose 4 and 5 electrons or gain 4 or 5 electrons. Normally, they like to lose 1 or 2. Yes, yes, always. No exceptions. Cores are solid. Yeah, I'm glad you brought that up. Yeah, only valence electrons come and go. We're adding electrons, we're adding them to the valence subshells, or we're taking them away from the valence subshells. Never, never core. Okay, I want to leave you with one thing here. Oops. Let's go back to sulfur here. Okay, I make a point of saying core valence, core valence. Now, there's a shorthand way of doing this, is that instead of writing out the core, because the core is always the same every single time. So what's the point of writing out the same every time? So what we're going to do is we're going to substitute one of the noble gases in place of the core. So what noble gas has that electronic configuration there? Neon. So the other way to write this would be like that. Sometimes they call this the abbreviated electronic configuration, but all we're doing is we're substituting electronic configuration for neon. So the way to do it, look at the periodic table. And you go up one row and look at the noble gas in that row. So we're looking at sulfur. We go up one row and look at the noble gas. So if we're doing sulfur, we're going to go neon in the last valence setup. If we're doing oxygen, we go up and write the one for helium. So that's a shorthand way of writing those core electrons every time. And just put in the nearest noble gas, which is up a row to the right. Now your next test is going to have this in it. But it's not going to be the most of the test. There'll be some questions on this. So it's real important to understand these first two, particularly. Okay, so we've done quantum mechanics in an hour, as opposed to a semester. Not exaggerating either, it's wild stuff. Okay, that's what I wanted to cover today. So,